Hello and welcome to 22nd lecture of course on data-enabled tribological engineering from experiments to predictive model. Topic of this lecture is a feature extraction and selection. In my view, feature extraction it's a kind of subjective knowledge. However, it is very important for this course and feature which will be extracted from different database will be depending on the complete application. So let me give you some sort of my views, and which we have already explored in previous lecture. So I'm trying to repeat few things again in this lecture. What we say that feature extraction and selection is it really crucial? I believe that feature selection is or extraction is mainly that variables. It may not be the wear loss, it may not be the friction loss, it may not be the lubrication effectiveness, but variables which are going to affect this. These are the also important. We generally say maybe there are 50 variables which will affect the tribological performance, but which variables are more important? That is what we need to extract from a database. Another one is that what are the relations and correlation between those variables that need to be extracted. That means we need to identify what are the complex relationships, and that for that purpose we really require ML or machine learning algorithms. What we do in this situation, we try to connect the historical data and experiential learning. This has been already explored in a previous lecture to some extent, but again I am trying to revise or remind this that these are important aspects so that we can anticipate future trend behavior and outcomes. We can say feature extraction is the first step toward the optimization. So this was also explored in the previous lecture. We want finally the performance to be optimized, and feature extraction plays a very important role. What is the really aim? We want to maximize information which can be obtained from a data or which can be obtained from a history. What we do with those data, we try to give some sort of model and train that model or train that predictive model more effectively using data, so that it can finally anticipate the future trend behavior and outcomes. So this line and this line again are the same. I'm trying to repeat. Overall aim is to reduce maintenance cost because we want economics, we want to enhance efficiency at the lesser cost. We want lesser investment and more profit. And then we want to go ahead with the timely intervention so that our machine should not wear out or it can be delayed as much as possible. And then we also want the resources allocation should be done effectively. So overall a lesser investment, more profit, that's the aim, and for that purpose feature extraction plays a lead role in that situation. And we want to also cultivate the culture of continuous improvement. Whatever we have done today, tomorrow will be better, and day after tomorrow will be further better. That's what a culture should be established so that overall results are in profitable to the society. We see that when we go ahead with the optimization, particularly for the real-time monitoring, and then we may require embedded sensors and then data captured from a sensors, processed through sensors, so that we can enable predictive models, and then those models also are able to figure out what are the bottlenecks and what are the areas which people have not already explored, so that we can explore more and then we can improve those models in a better manner. We say feature extraction and selection techniques are integral component of a data driven insight, which will be explored from 23rd lecture onward. It is really important for predictive analytics, and it contributes more like to go ahead with the effective decision making and continuous improvement, which is what our main aim when we are applying the machine learning algorithms. We also say that predictive maintenance relies heavily on a feature extraction, because which parameters are going to affect the solution. If we are not able to extract, we are not able to understand, or effective maintenance cannot be applied, or predictive maintenance cannot be achieved. So that's why we say predictive maintenance rely heavily on feature extraction, and when we say embedded sensor or sensor which we are connecting with that, as well as on the monitoring technologies, whichever monitoring technologies we are using, because day by day the monitoring technologies are enhancing, getting better and better. In this case, what we say, it uses a real-time data to access the current condition of equipment, predict when the maintenance is really required. So we do based on the condition based maintenance is what we are emphasizing. We do not go ahead with the predetermined after 5 years component need to be replaced, after 10 years need to be replaced. It can be after 5 days or it can be after 50 years. That will be based on the condition. So that's what we, for that purpose, we really require a sensors, and then maintenance strategies or models, predictive model, which are able to estimate when the maintenance is really required. So what we say, the advantages of the feature extraction: we are able to reduce the dimension, we are able to reduce the noise, we are able to improve the model, and we are able to bring more like interpretability or user friendliness in this case, and then we are also able to improve the computational efficiency. Reason being, we have generally get a large data set. We have a lot of publication, a lot of books, a lot of data set available, and if we are able to utilize this feature extraction technique, we will be able to really extract the relevant feature which are important for our application. We don't want all 50 features, we don't want all 100 features. So that will really reduce the computational complexities, and then it will simplify our analysis also. Similarly, noise reduction, many times like we have suppose 50 features, and we know that only 5 features are contributing 95%, and 45 features are contributing only 5%. So for us, this 45 features are going to make a noise. So if we know very well, if we can try to control those 45 features, that will be unnecessarily expensive, and it is not going to give overall effectiveness to us. So we may concentrate on 95% contribution which are coming from 5 features compared to the 50 for other 45 features. It says it improves the model performance, reason being that we are able to reduce the dimension and overall simplify the model, and if there is a simplification of model, understanding will be better. It can be said that model gets generalized, which can be utilized in a proper way now. Otherwise, we say that in we are able to understand these models more better manner, making it easier to understand and think about what are the patterns which are really followed in a data. So this is essential for the field of tribology, where physics of the wear and friction is critical. This is what we say, almost every application there is a somewhat different friction and wear happens, and we need to understand using this kind of analysis, using the data and understanding data, predicting the providing the predictive model in the situation. Another one, we say that in most of the cases number of features are many, and that will reduce the computational speeds. So we try to reduce the number of features, increase computational efficiency, and then we really go ahead with the proper constraints or proper then the variables which are really important for the real time management or real-time condition monitoring, so that overall resources are effectively utilized for our application. We say feature extraction in a process in a tribology because as I mentioned earlier, tribology is very complex and we need to understand for that purpose, because we have many variables, which variable will play major role, important role, that need to be accounted appropriately. So we say the analyzing tribological features or tribological data, which may contain friction data, wear data, lubrication, vibration, forces data, and then we are trying to gather from a different source resources, so different sensors. Sensors can be thermocouple, accelerometer, strain gauges, and many more. One thing is that when we are connecting with so many sensors, So data fusion is important. Another one is that the synchronization of those sensors are also important. So this is was also mentioned in previous lecture. Again, I'm repeating same thing in this case. In addition, we need to learn from a database also, and then we need to extract that information, what is available in literature, and now what is the interpretation, how do we really make a model from those available literature. One of the major thing is that most of the data contain the noise and irregularities. So we say that before going for the really analysis, before going for the making a model, can it be a filter, or can we go ahead with the filtering so the noise removal happens and data alignment happens. This is another important thing, data alignment. I'll show you one of the gear slide where the data alignment was done in our lab, and I will give that example, of like describe that example. So in this case, what kind of filter we use? We sometimes we use a low pass filter, sometimes you has high pass filter and band pass filter. Particularly these are the frequency domain filters. We try to make a high frequency, low frequency, band pass frequency, and so that overall whatever the relevant feature we want, we can extract that. Because when we are acquiring the data, we get a lot of information, but whether that information is relevant to us or not, that comes when we start using our domain knowledge, our expertization, our experiential learning. Then only we can extract the data appropriately. So that's why we say for feature extraction, domain knowledge is a must. It's not just a number. It's not a number game, it's a knowledge game. So what we say that in this situation, these are the first filtration. Other one, particularly when now in these days we are talking about images. In that case, we know that median filtration, valid denoising filtration is now getting more popularity, and they remove unwanted noise while preserving the essential information. So that's why the valid denoising technique or median filtration is important. As I mentioned, that synchronization is important, and I'll be elaborating that in one of the slide which will be discussing the gear case. We say the features may have variations. We can say we have a time frequency representation, frequency domain representation, and this is what I was mentioning: the low pass frequency, high pass frequency, band pass frequency. Often we connect with the frequency domain attributes. We also have time domain statistics, where we go ahead with the synchronizing. In this, synchronizing is really required, because we know that when we go for the too many data, and that data contain the noise, and if it is a periodic and we are able to synchronize the periods, the first period, second period, third period, fourth period, and we can take an average. So if you have more and more data, it will give better and better average. I'll also elaborate that. In this case, again, we are saying that choose the most relevant feature which can really provide a domain knowledge, preserving the essential system characteristics. And last one is a visualization. We need to also replot or plot the data, and it can be a time series plot, which we showed in also previous lecture. It can be a spectrogram, which we will be also showing in this case, or it can be heat map, basically to show the some sort of relationship and its variables or dependency on the parameters. It can be represented in different manner. So what is this is the overall feature extraction process. We try to analyze the data, we try to denoise it, we try to extract the features which are important, and then finally present those features in a more meaningful manner. So let's take a example of the gear vibration case. We see that this is the gearbox. Here the Z is shown as a number of T, Z1 is a number of T, Z2 is a number of T, 3, 4. Coming to the F1 and F2, they are and the mesh frequencies. What is the importance of mesh frequencies? Because mesh frequency are completely known to us. Whatever the sharp frequency and mesh frequency will be related to that. That means before the event itself, we know what kind of mesh frequency we are going to get. If we are getting a signal or getting a harmonic of those frequency, and then how do we analyze, how do we extract the feature, that will be explained in the next few slides. So another one is a temporal feature. We get data directly from a sensor. We can plot on the time scale. That's what we call a time domain characteristics. Now here we also get some information. We know that if the vibration level is increasing, or if the wear level has increased, which is increasing vibration, or friction has increased, which is also increasing the vibration, or periodic motion, then we can figure out what is the value of the mean standard deviation, skewness, kurtosis, and any other time domain statistical measures. Based on those values also we can find out what is really happening. We can figure out condition of the machine itself. So this is a temporal feature. Based on the time data we can get also information. However, I am giving little more focus on the frequency feature because that provides a little more information to us. We are saying understanding required information about frequency content of signal is kind of comes from a literature. We know the what kind of frequency response we are going to get from gear, what kind of frequency response we are going to get from ball bearing, what kind of frequency response we are going to get from seals, what kind of frequency response we are going to get from a sliding bearing. So these are well known. So we are going to extract the information from history or text which is already available, and based on that we are trying to fuse, maybe say we are connecting our data which we are getting from a sensors. So we say obtain signals in a frequency domain, because time domain we get, the temporal feature we get, we use FFT to convert that in a frequency domain. That's why we are saying this obtain signal in frequency domain using a Fourier transform or wavelet transform, whichever. In this case we go ahead with the Fourier transform. When we require both the time and frequency, we go with the wavelet transform. Now this provides insight in dominating frequency, its harmonics, and other spectral properties. This is what I am just trying to give. Now suppose the rotational frequency of the shaft is fz. Now in this case, because we know the harmonics also will come, naturally I will get a response on 2 fz, I will get a response on a 3 fz, I will get a response on a 4 fz also. So this is already known. We should get some response. And now if I am getting higher response at the 2z, 2fz, what is the meaning of that? If I am getting higher response at a third harmonics, what is the meaning of that? This is already well documented, well established. So we can connect with that. Of course, there may be some deviation, there may be some possibility that may not be having 100% correct data results, but at least we have this information available and we can quote and we can connect with that. Let me give a little fundamental knowledge about a vibration. We say every tribal system either involves sliding or rolling, and whenever this mechanical system involves the sliding and rolling, vibration becomes inevitable. Vibration will occur, and this is what has been shown a pillar, and in this case you are able to see vibration will occur. Of course, in this case we are showing a high magnitude and maybe much lesser. That's why we say systems with inherent inertia. Most of these systems have a mass, so inertia will be there, and stiffness. Again, they have some sort of rigidity. So if there is a inertia, there is a stiffness, it will oscillate about their equilibrium position if it is disturbed with the external force. And we know very well in tribal system, disturbing force are bound to happen. So this is what we are saying, that disturbing force in our case will be rubbing forces. It can be rolling bearing, it can be gear. Even the disturbing force can be misalignment. So we will get also response related to misalignment. It can be unbalanced, it can be induced vibration also. Now we see why vibration once generated will be transmitted through the structure to the medium. That means that even at the interface some vibration is happening, it will get transmitted to the outer surface, and if I fix some accelerometer to the outer surface, I'll get some response. Of course, there is a possibility it may get damped down to some extent, but still I will be getting a response. So another one is that we know the natural frequencies of the system, and then we get a little more response of the natural frequency, and that's very important to us to understand and get the response. Vibration magnitude can accelerate the wear rate. Of course, if there is a vibration, it will also accelerate the wear rate, and if there is a wear, there will be acceleration. So they are connected with each other. Once we get a response, we can really do some sort of analogy and connection and establish some relation in this. I'm just showing some sort of vibration signals which I also showed in a previous lecture. In this case, we are showing this is a one revolution of the gear. Number of teeth may be 55 or something like that. Now, if this gear gets misaligned, so we are looking at the trend analysis. What will happen? Because of the misalignment, somewhere the vibration, this amplitude will decrease, somewhere vibration will increase. So we are able to see the waviness in this kind of profile. Coming to the one gear, naturally the some gears will have a high amplitude, some the gear teeth will have a low amplitude. So I will not be getting kind of the symmetric, in this case what we are getting response, in this case we are not getting, in this case we are not getting that kind of response. So the gear teeth response in this situation, and if the teeth is fractured, we will be getting the one gear teeth high response. Just before and just after that we will be getting by response. So this is kind of a trend analysis which we can done, or sometimes we try to superimpose each other. It can be a comparative analysis. Sometimes trend analysis also been mentioned that initially it is a good, and after that this response starts. That means initially the vibration is something like that, and then suddenly increases. So this also can be utilized as a trend analysis for purpose. In this case, what we are analyzing in this case, this is some sort of gear teeth configuration. A single stage has been given over here with a lubrication condition. It can be analyzed from that angle also. Now, this is what I mentioned about the trend analysis, that we are getting high peaks, then low peaks, and then low peaks, and further high peaks. So this is the kind of one rotation, this is a second rotation, this is a third rotation. This can be done. Now, here we are not able to understand much, but if we go to the frequency domain, we are able to see, yeah, peaks more or less comes on this frequency, this frequency, this frequency, this frequency. And if these frequencies are characteristics frequencies of the system, then we will know what kind of a really response is coming out. Now suppose this is a first harmonic and this is a second harmonic. So in this is a first rotational frequency, and then this is a 2 times of rotational frequency. If this kind of response comes, what is the meaning of that? We are getting more and more misalignment. That means we need to correct this misalignment. This is important to understand. Now how do we convert this time signal to the frequency signal? Often there are a number of theories been given. We say that every time signal will contain this the functions of the frequencies, which are the system frequencies or maybe component frequencies. That's why it's being given here omega t to omega t. This is the harmonics and all, and these are the phase angle mentioned. So overall response we will be getting this way and can be divided in separate responses. So this is what we call the phase difference will keep coming. That's sort of phase 1, the phi 1, phi 2 and all, and they get once we do FFT, it really comes out to be very well. Now question comes, how do we denoise the vibration or we remove the noise from signals? So that's for that purpose we say FT gives the average characteristics of signal during whole cycle. For better accuracy, what we do, we take a number of data, and if there is a repetition of the data, then we will average it. On averaging, noise will come down, will reduce. I'll try to explain that. I'm just showing a one gear teeth, something like this, and then we can get a number of data points on this. One data point, another data point, another data point, another data point. Of course, we don't physically divide. It is basically based on the frequency or how fast we are getting the data in one time period. And we know in maybe say 1 second how many rotation of the gear shaft will occur, and in that how many gear teeth. So based on that we can calculate. For that purpose, let me take an example over here. We say, let's assume rotational speed of the gear is which has a 18 teeth is a 6000 rpm. That means the shaft which is rotating, it is rotating at 6000 rpm, and it has a gear which has a 18 teeth. Now if we really require the data to be captured, so we say that this means we require a minimum 100 data. That's what I'm dividing by the converting in this case per second to record one data per rotation. We know that 1 minute has a 60 seconds, and then we want to record 100 data per second for the per rotation, because we know very well it has 100 rotation per second. 6000 divided by 60, will turn out to be 100 rotations, right? That means 100 rotation per second. Now if I want to really record one data per rotation, I require a minimum 100 data per second, and this is what I am just trying to convey. We don't really physically divide the gear teeth, we think from a data point of view. Now if it has 18 teeth, naturally per teeth, if I want to capture one data, I require 18 into 100, that means 1800 data per second, so that I'll get a one response per teeth. Now if I assume that gear teeth is a symmetric, this if the midline suppose, and this is a symmetric this side and this is symmetric, and we require every time, this is 1 2 3 4 5 6 7 8 9, this is a 10, suppose 10 points. Now we require 10 points and it is symmetric. This means we require overall 20 points. That means I really require to get a capturing of the 10 data of the one half of the gear teeth. I require overall 36,000 data per second. This gives a frequency, that how and what frequency we should capture the data. And then sometime if we want to capture this frequency, we multiply with a Nyquist frequency, and then we say that we should get this many data to get a really reliable results. Now when we get this kind of data and we get to say the number of cycles, in one cycle I am getting the 36,000, another cycle I am getting 36,000, third cycle I am getting 36,000, or maybe say instead of cycle in the per second in this case. However, depending on if I convert to the cycles, when the one cycle is getting completed, one second cycle is getting completed, third cycle is getting completed, and we know that after every rotation the same point will be coming again and again. So this cycle, second cycle 2, cycle 3, if I get a 25 cycles and I average, the noise level will come down. But how do we do that? How do I know that every cycle will have the same number of data? So this is what we need to really see. For that purpose, this is what we call a synchronization is a must. What is the meaning of that? If the shaft speed we are assuming is 6000 rpm, and number of data which we really want is at 36,000 per second. Now quite possible, because of the change in speed, because motor speed doesn't remain constant, it doesn't remain constant. Maybe of course there are some motors which are well controlled will remain, but unlike what motor we are using in our lab, it doesn't remain a constant. Sometime it may give a 5999 rpm, sometime it may give us 6001 rpm. So that means in this situation, number of the data which are going to vary will be around 6. Now it is very difficult to control exactly the speed of 6000. So that's why we say that maybe I'm assuming in this, in one cycle I may get the 36,000 plus minus 60. That means in cycle 1 I'm getting 36,000 data, in another one I'm getting 35,940 data, and third cycle I'm getting 36,060 data. So this is information will keep fluctuating. Now what will happen if I start averaging one, I may get a more garbage. That means because of the variation in rpm, I am going to get a very bad data, and that's why the synchronization is required. And this whole phenomena says vibrational signal must go through time synchronizing averaging. Now here we are using the accelerometer to get a data. In along with that we use a key phaser also. Key phaser is gives the information about completion of the one rotation. Now instead of 1 second, here I am using the word, now we are getting per rotation 36,000, and in per rotation 36,000, sometime the rotation is getting completed earlier, sometime it is getting later. Now if key phaser is there, and that provides me the data, yeah, one cycle is getting completed, in one cycle I am getting 36,000, other getting lesser, other more. So this information is already available. Then we do a digital resampling. What is the meaning of digital resampling? We try to convert each cycle the same number of data. So in this case 36,000 will it be maintained. In this case number of data point have reduced, so we will stretch it, and then we will make in a show that first point and the last point are same, and then we do a kind of extrapolation to get a results related to that. In this case, we try to get interpolation so that we get a 36. So in each case, this is a digital resampling, is analog sampling which we are getting. Now here we get almost every cycle will have a same number of data. Now here averaging 1, averaging 2, averaging 36,000 will not be problem, it will reduce the noise. That's what we are saying, that the time synchronous averaging. The time synchronous averaging is very important whenever we have multi-sensor. It will really help each other, and then we should get a more or less similar kind of information and correction in this case. So that is important. Now after doing this, once we have done synchronized averaging, after that we have features. In this case, we can get a mean value, standard deviation, particularly the time synchronous averaging has been done, skewness, kurtosis. This is what we have already learned, and we are given importance, particularly surface softness. In addition, there are other factors which in this case, a 2003 paper, feature extraction and classification a gear fault using the principal component analysis, which was published in 2003. They use a crest factor, they use a shape factor, they have used impulse factor and clearance factor also. So here they are giving 10 features instead of the 4 feature which we initially thought about. Now in this case, they are comparing 3 cases. When one case is a normal teeth which is not a worn out at all, is a new one. Other one, there is a some sort of crack in one of the teeth, and last one is the third one, that one tooth is completely broken, and then we will be getting different response. So this is the normal teeth response which they are plotting. This is the second case, a tooth is cracked, and that's a the signal has come, and last one is a tooth is broken. So there are 3 signals, and then we need to analyze it, and these are the features. Of course, all the features are temporal features. We are not starting yet frequency domain, it's only the time dependence, and they plotted the results. Now here you can see the blue colored dots are the normal gear, red colored triangle is a cracked one, and then broken green color is square, is something like a broken gear. You can see standard deviation, you can skewness, kurtosis, peak value, mean value, and RMS value, crest factor, shape factor, impulse factor, and clearance factor. So we are not able to differentiate much in standard deviation because there is a overlap. Skewness also, there is a lot of overlap. Kurtosis gives a totally different value. Here the higher value is coming for the normal gear, which is quite contrary, and then it may not be useful. Then comes RMS value. RMS also there is some sort of overlap. Now, what are the remaining features? We have peak value, which is clearly indicating the broken gear is giving a maximum vibration. Then comes the crest factor. This also same thing, broken gear is giving more vibration. Shape factor, the broken gear is giving more vibration. Impulse factor and clearance factor also is giving that. That means we need to think about whether we really require these features to be selected, so that for the future we do the analysis based on that. So that's why they say that crest factor is important, shape factor is important, and impulse factor is important, and clearance factor is important. So we consider those factors for the analysis. That means we are trying to extract these features, and then other features can be removed for the time being, because we are not getting any clear idea from those features. So there's no need to really extract all the features. We require 4 features or 5 features, where maybe the results based on that can be giving some sort of predictive model. Now what this was a time domain. Now coming to the frequency domain, as I say that we use a number of filters. One is a low pass filter, high pass filter, and band pass filter. What's the meaning of that? We allow lower end frequency. Here these are the allowed, and here we are using the filter. This is a cutoff frequency. Any response which comes on the higher side will be eliminated. So if we have a number of data, we will be converting to the frequency domain, and then we eliminate high frequency data. That's a current we stop it, that the high frequency signal will not be passing. Coming to the high frequency filter, in this situation only high frequency the data will be passed, low frequency data will not be passed at all. So that means this data will not be acquired. And sometimes we know the kind of gear mesh frequency, and we say there should be a band pass filter nearby that, so that I get only those data. That means if there is a, suppose I required a 500 hertz some signal, and I'm giving plus minus 10% to that, that means a band pass filter will give 450 to 550. Any signal which is passing having this frequency domain, only that will signal will pass, other signals will be completely removed. That means I'm very focused at what signal I really require. If this signal is coming, then only it makes sense to understand, yeah, something is going wrong. Otherwise all, because noise has so many frequencies, and we can eliminate all those. That's why we say, as a gear deteriorates over time, structural integrity of the gear deteriorates, resulting in a decrease in a load carrying capacity and rigidity. Stiffness also will come down. That will increase the chances of vibration amplitude. And here one more term is coming, sideband will start near the gear mesh frequency. That means this is a sideband. If we know the gear is when getting worn out, it will have a more sidebands. And if we are able to really figure out what are the sidebands and how many sidebands are coming, and we do predictive analysis based on that, that will make a much more meaningful results to us. So what am I saying in this case? Now here as I said, that gear mesh frequency, which is a really a fundamental frequency associated with the engagement and disengagement of the gear teeth as they mesh in one rotation. And then we have so many teeth, suppose again 18 teeth, not all 18 teeth will be engaged, maybe sometime only one, and sometime two teeth will be getting engaged. When engagement and disengagement, that is will be a kind of a phenomena. And if the shaft frequency is something like fr, rotational frequency of shaft fr, and number of teeth is n, so that means first the fundamental gear mesh frequency will be n into fr, and we will be getting harmonic of that. That is, I will be getting a response of the 2 n into fr. I will also get a harmonic of 3 n into fr, 4 n and fr. Now I may get a more and more and more, but are we interested? If you are not interested in the fourth harmonic or more than fourth harmonic, I can use the low pass filter. I say, yeah, before and then the higher than maybe say 8 NFR, I don't really require any signal cutoff. That's possible. So this is where we really require to have some domain knowledge, and then how much frequency should be set, what kind of filter should be useful for that purpose, that need to be understood, need to be clear before starting. Now coming to the sideband, which we started maybe mentioned in the previous slide, it says that modulation and appearance of sideband can be caused by various factors. One is that a change in a gear load significantly, there is a misalignment, there is some sort of a tooth damage, and that is what we wanted to achieve. Because in my case, my thinking, the gears of misalignment is also fault. So we should diagnose that. Tooth defect is also fault, we should diagnose. If there is any lubrication drag case, that will also give a response. And if there is a shaft is getting eccentric, little eccentricity is coming in shaft rotation, that also need to be accounted. So this all will give us sidebands to us. So what we say, by identifying specific sidebands and their pattern, analysts can pinpoint the root cause of the gear related issue and plan maintenance or corrective actions accordingly. So it gives information well in advance to us. Now one point comes, I know the gear match frequency is there, it has a harmonics also, and I know that pinion also will have a one kind of response, gear will have another kind of response, because the gear shaft and pinion shaft will have a different rotation. If they have a different rotation, naturally NFR all this will be different, this will be different. Now in this case I say NFR, in this case I can say NRF 1, 2 maybe, because shaft frequency will be different. Do I really require a response as a fundamental natural frequency? No, not necessary. So what they do, they go ahead with the residual errors. What is the meaning of residual errors? So that whatever the difference is coming, I have a healthy gear, I get a response, and I know that the gear has run maybe say 1000 hours. and it gives us some response and some frequency response. I we say subtract that response and come up with only the residual errors. Now, if there are residual errors or there are sidebands, I can analyze this and I can get a better results from this. So, this is important to understand. Sometimes we require a main response, and sometimes we say no, main response already I know from literature. Why do I again see it? So why not I go ahead with a residual error? What is the thing which was not earlier? Now with the time that is appearing. If I get that, that means I'm reducing the overall the feature which need to be extracted, and I get a lesser number of the features, and I can analyze those in a better manner. So this is I'm just trying to show one analysis. This is the time frequency averaging being done, and the shaft was vibrated, maybe say run for the 25 cycles, and then it was plotted. We got the raw vibration signal. This is a key phase signal or reference signal. TSA was done on that, and then as I say that we are more interested in only in difference in a signal, residual in a signals. So we were plotting pinion residual signal, gear residual signals in this case also. So in this case particularly you can see the residual signal and the pinion case, because pinion is more has a more chance of the wear out. Of course from a contact point of view, pinion and gear has the same, but I have seen mostly the pinion gets a little more damage compared to the gear. In this case you can see here residual initially at the 0 hours. You can this is a noise, this is a noise, this is a noise, and this is a noise. After 40 hours I am getting somewhat little difference in response, and here it has been shown as a 24 teeth in this case, and then it has been plotted directly on a gate surface. Here we are getting some response, and here you can see here it is getting shifted to the one side. That means there is some sort of wear and some sort of clearance has been created, and because of the clearance it is getting shifted. Now this clearance is also important. I showed in previous slide clearance response. You can see here there is a clearance factor also. So there is a clearance factor. So we, if we know the gear teeth have a the mashing has a more clearance, that also is a response. And here that's why I'm showing here in this situation that it has getting shifted here. And when we after 100 hours of operation we open up, and then we found there is a some sort of edge loading and some sort of the pitting formation that has occurred at the here in this spaces. So this is important to understand. Somewhat variation, as in we are getting only the residual signal and we are plotting residual signal, and that in a frequency domain, that is really give the some sort of response to us. Now what we talked about vibration earlier, but there are other things also, particularly for acoustic signal, which is also very important. It helps really in a many ways. Now a new thing is coming, a digital image correlation. We take a pictures and try to correlate and then draw the data from that, and then that's why we say there are no many sensors. It's not only one or two kind of sensor, there are many sensors, and it's not only the vibration signal need to be checked. If there's a acoustic signal, that also can be checked. If there's a temperature also can be checked, or maybe say eddy current also be checked. What will happen because of this? Earlier what we used to think about a non-destructive testing. If I have these sensors and in situ I'm able to get a data, I don't really require those machine. By embedding sensor, by installing sensor, all non-destructive testing can be done in situ in the machine itself. So that's what we are trying to do, that kind of thing here, and we are trying to monitor. So we say that we do vibration analysis, oil analysis. Of course we have a thermal imaging camera also, that also gives a good response. We can go ahead with the vibration analysis, and then in this situation particularly, whatever the wear particle, engine oil, this gives a good response to us. And on my next two slides I'm going to show more and more on oil analysis. So vibration analysis I already showed, oil analysis I'll be showing in next slide. So this is what we try to do, condition monitoring of spur gear. Why we are doing condition monitoring of spare gear? Because we want a condition based maintenance. It's not a preventive maintenance or time defined maintenance. It's basically condition based maintenance. So I can divide maintenance technique into, we say that it can be a time dependent maintenance, it can be time independent maintenance. There are two categories. Time dependent techniques may be that we know the preventive maintenance after 5 years, after 5,000 the kilometers we need to change oil, something like that. Or another one is that we keep looking at the condition, whenever there is a need of the change, then you will change the oil, we change the bearing and those kind of things. So this is a condition based maintenance. Time independent is something, okay, component failed, we will replace it, and then replacement is not that difficult. It's something like car tire punctured, we will replace it with another stepney, something like that. So what we are using in this case, particularly when think about the condition based maintenance, we say diagnostics is are important, prognostic is also important, and we need to find out the what is the really probability of the fault. For that purpose, we really require continuous detection, isolation, and identification of the faults. Once we identify the faults, then we try to figure out what is, how the people have done earlier in history, and how it can be solved that way. So that is what important thing comes. Now I am just showing the oil analysis two results. You can see here distribution of iron ppm and wear mass, and this has been shown wear mass in microgram and fe ppm in the with the blue color square. When we try to find out, we seen a three situation. One is that the pure oil without adding HCl, then we do accelerated test using the some sort of acid, that's a weak as a HCl, and then in addition we go ahead with the nano additives, because in the lecture 15 we learned that nano additives really improve the performance. It acts as an anti-wear as well as EP additives also, or extreme pressure condition can be handled using that. So that's why we use three situations. First case, in this case you can see here, when we are going with without HCl, and the FePPM level is only the 2149, while coming to the wear mass is something like a 66.7 milligram. Coming to the HCl, this Fe ppm level has increased to 8875. Of course, weight loss is also on a higher side, is something like 73.9 or maybe say 74 milligram. Coming to the nanoparticles, here we find that again the response has come down. In this situation, particularly Fe ppm level has come down to 6000 from 8800 to 6000 only, and number of this wear mass also has reduced in this situation. So nanoparticles really help to reduce the response. Now if I compare with HCl and nanoparticles and without HCl, we are able to see Fe ppm has increased, but wear mass has come down. That means there is a change in the particle size also. So we really need to see the response. Now here indicates very clearly this only the not a Fe ppm or wear mass, we need to also see the size. So for that purpose we use another sensor, that's a we are using some sort of a sensor in a wear mass online sensor suite, and we are debris metallic sensor in our lab. You can see here the 40 to 60 micron response number of wear particles. In this first is without HCl, with HCl, and with HCl with nanoparticles. Here you can see this is only 57 number, 26 number, and 1126. That means number of particles which are in the range of the 40 to 60 micron are higher with HCl and nanoparticles. Now coming to the second case, particle size ranging from 60 to 100 micron, we are able to see the without HCl roughly 3000 particle, with HCl we have around 4726. Coming to the with HCl and nanoparticle is a huge number, is something like a 16,600, is a huge number. So one point comes in the situation, oh, is it a nanoparticle is a bad or good? That's not very clear to us. Here reason being that this is given higher side, but coming to the next one more than 100 micron, You can see more than 100 micron. This first case without SCL case, it is giving 20,000 particle. What with SCL and nanoparticle, it is giving only roughly 2,000, so 1/10 of that. So this is important. So only looking at the FePPM may not give a complete results. We are looking at the wear mass, we are looking at the number of particles which are getting generated. So for complete comprehensive analysis, we really require more number of parameters data, and then we require many data, and then we extract more relevant data for our purpose. So this is the beauty of our analysis: make a system complex and extract a feature to make a system simple. Increase the complexity, use feature extraction, so that we get reliable results, and we simplify it also. So both the things are important for us. And now if I try to review the feature extraction, this is also available in one of the article which I am just showing. They are using about the wear analysis and oil performance. In addition, we also look at the vibration analysis, which is a traditional. If you look at the more paper and more books, they go ahead with the vibration analysis. However, people say that vibration analysis comes as a later part. Wear analysis and oil analysis come the first. So it doesn't matter to us, we want all three. We did a vibration analysis, wear analysis and oil analysis, and here in this paper they use a wear analysis and oil performance analysis. What they are trying to figure out, what are the wear mode and causes, what are the wear components, what is the wear degree, is the severity level, what is the evaluation process of the wear, what is the performance, what is the deterioration, and then what are the residual products, what are the contamination level, what are the degree of contamination, what are the causes. So these are the things which they are trying to extract the features. Now it depends, every author has a different way, every expert has a different way to extract the features. It is a basically expertization based, it's basically a domain knowledge based, and what we want to achieve. So feature extraction from one author to other author will vary, but techniques will not vary significantly, which we are mentioning here. Wear analysis, oil analysis, vibration analysis is not going to change significantly from one author to other author in this situation. Now we try to summarize this. We say feature extraction process in a tribology. Now in these days we are talking about the digitization, we are talking about the image capturing, or in the future, as I believe that most of the sensor will be digital image correlation sensors. I have not used this, but this terminology has been now in the literature and people have been referring this. I know that it's developing algorithm, cleaning image, so that it is really required. So we'll have a next 14 lectures will be giving some information on that. For this purpose, for in a present lecture, I'm trying to do some sort of overview or introduction of that. So what we say, to observe in situ one surface, tribology surfaces must be converted into digital image. Something is in the black box, we take an image and try to analyze it. If we are able to analyze it, can we really figure out what is the wear out? So examine image for purpose of diagnosis, so that we get a surface condition or insight into surface condition and relate it with the wear patterns. If it is possible, it will be good. So I am just trying to introduce the subject here. But what are the challenges in this situation? So it is a good hypothesis. So keep capturing the images, which is easy, and then converting to the dig out the surface features, and based on surface feature you can say, yeah, there is wear out or not. So challenges in this case is basically extraction of the picture or whatever the feature, and which most effective feature should be captured. Of course, it will require more analysis, more research in this case, and then we try to distinguish image classes. Like, we do have wear debris 6 types, 10 types, 12 types, 15 types. It depends on the person to person. We divide in 6 types, and then we say, oh, this kind of wear debris means this kind of wear will be happening, and that need to be reduced. That means we need to change this kind of lubricant, or this kind of, if there's a misalignment or something, some corrective action based on that. So what are the steps in when we do this kind of image analysis, converting this surface, capturing the surface into image? What is to be done? We say we require image acquisition, pre-processing of image, then feature extraction from image, then feature selection from image, and finally comparing with the morphologic. Now, what are the things which are already available in the literature? So, when we go ahead with image acquisition, naturally we require high resolution camera which can really capture the surfaces or lubricant droplet or maybe the wear debris particle which is there, that need to be captured. Now, it can be if we are able to embed, microscope is good, or optical profilometer is very good, or high speed camera. I believe that high speed camera or good camera is easier when compared to other. High speed doesn't mean we go for 10,000 frames. It can be 54 frames per second or maybe 90 frames per second. I think that will be sufficient for us. Coming to pre-processing, because these images will be containing some sort of noise, so we need to think about how to go ahead with the noise reduction. So that's what we use a word earlier, that wavelet can be utilized to reduce the noise of the images. And then based on we need to go ahead with image enhancement, and if there is a need of color, we do color correction, but often I prefer to go ahead with grayscale, because that requires a lesser information and it will be faster processing. Coming to the feature extraction, we need to extract the feature what we want. It can be wear volume, it can be surface roughness. Of course, we know that if the surface roughness is extracted, wear volume can be calculated, or sometimes you want to find out what is the film thickness on the surface itself, that can be extracted. Now, here in this case again, when we talk of the film thickness, we need to connect with the other earlier images also, so that's important. Now, there are a number of techniques which we say the edge detection technique, texture analysis technique, or color analysis technique. This can be utilized for the feature extraction. Coming to the feature selection, that will begin depending on the kind of expertization, domain knowledge. Person may say that I want to go with the wear analysis, I want to go with the friction analysis, I want better lubrication, and that need to be connected with the existing literature, what is available in a literature, and how do we correlate with that. Let me take one example on this. We captured the V4 ball image was shown earlier to you. In this case, we have captured this image. Now, we converted this image using the MATLAB code, which MATLAB has a very simple code. We import the image and then we convert the grayscale image as such. After that, we are trying to find out what is the value of roughness, assay value, SQ value, skewness value, and kurtosis value. As I already mentioned, that when you go for the 2D, we go with RA value, RQ value, and R skewness in this case particularly, and then kurtosis. This is for the 2D case when we go for surface profilometer. When we are going for 3D case, we will go with the assay, SQ, skewness, and all in this situation. So, another one, why we are converting to the gray scale, reason being the gray scale image has a single channel representing intensity is compared to the 3 channel red, green, blue, which is for the color image. Now, when we convert it, we are reducing the complexity of the image processing algorithm. It will be computationally more efficient. So, we want more and more faster results. Again, we in this case assumption is that color information is not going to add any information to us, it is not relevant to us. So, if it is not relevant, why will I go at the color information? So, gray, and moreover gray the scale can enhance the contrast and focus on intensity variation in image, and we can calculate those. It is we can use edge detection and feature extraction technique directly on grayscale images. In addition, we are saying it is also advantageous because it is a less sensitive to change in illumination, because when the we are capturing image, what is the light intensity, colored image will be affected with that. If it is a color intensity variation is there, then grayscale image will be better option compared to with this one. Now, here but we use the word we are getting assay value something like a 0.45693, SQ value we are getting 0.58831, skewness we are getting 0.26225, kurtosis we are getting 1.53137. This doesn't mean micrometer, it is giving some value. So, here the characterization is also required. As I mentioned with the morphological analysis, if I measure one image and I correlate what is the meaning of 0.45693, Is it a 50 micron? It is a 100 micron or what? So there will be some sort of correlation will be required initially. So whatever we new thing we do, we will get some response, and we need to do a calibration. If the calibration is done, then after that whatever happens into the system, that will be relevant to this or maybe related to this. Initially we are getting some values. This is intensity related, it doesn't have value as such. Now we need to correlate with a actual measured value. If use a first profiler meter, we do a calibration, and as is the same thing when we make a new sensor, we do calibration, and then based on that calibration reading we give some sort of plot or some sort of a curve. Same thing happens in this situation also. Whatever we try to relate what is already available in literature and what we are getting, what is the correlation between this. If we are finding, then only the subsequent data driven approach comes. So that's why this is important to make a course come up with a innovative model and correlate with a historical whatever available to us. So we measure in this case and connect with that. Now if I want to go and replot this kind of image what we have achieved, we can get also image in this case, and this is a surface roughness profile. Again, this is, as I say, the relative one, and if we are trying to show the two different images with the different angles, this can be plotted in this manner. So roughness can be plotted, can be measured. Again, quantification is a must. Without quantification it will not give a good results to us. It's very necessary to understand. Now towards the end, which this principal component analysis has been mentioned in number of books, number of articles. So I'm just again trying to give you some sort of overview. This is what we say, the PCA is a widely used dimensionality reduction technique. We try to reduce the dimension using the PCA. Aim is to transform high dimensional data set into lower dimensional representation while retaining essential information. That's the main purpose of VCA. And then what we are doing, we are trying to figure out main features. As we were mentioning about the feature extraction, here we are trying to come up with that only. We say find principal component which are very important. So linear combination, of course, again the PCA has one of the major drawback, it's a linear. Most of the algorithms we are using is a linear, so that's why we require a more detailed analysis, we require more data points. The linear combination of original variables, here again we are trying to figure out only the variables, not a wear, not a friction, not a lubricant. What variables, how they are affecting the response of friction, response of wear, response of the lubrication, and those variables are really independent or not. So PCA ensures those variables are independent. Say ensure this component capture maximum variance in descending order. So we do a kind of analysis and we give a representation in descending order. Say variable 1 gives a 54% contribution, variable 2 gives a 34% variation, variable third maybe gives a remaining, means 100 minus this 88. So that's a 12%. So we do this kind of thing. Or if there is a variable 4, then that will be also there, that can be done. We will show you the one example in this case. So what are the steps in performing PCA? We do standardization. This was also mentioned in earlier lecture. Whatever the data, they are generally given in a various units. Standardization is a must. How do we do standardization? We make a standardization by making mean 0 and unit variation. Variance will be 1 and mean will be 0. If you are able to make that, then it makes sense. Otherwise it is not. Reason being, we were looking at the film thickness in a micron, wear volume in a mm cube, friction in a just 0.25, something like that. Now we know everything is different. Now RPM and the rotational speed RPM and the meter per second velocity, Newton, load, they cannot be connected with this easily. So we need everything to be converted as a 0 means and unit variance. Then only the standardization comes. Ensure equal contribution of each variable to the PSA. Let's say that it should not get affected with a value. Some value is 1000 and some value is a 0.1. It should not happen that 1000 is always higher compared to 0.1. But because we are changing the units, things will change. So to avoid that kind of thing, to make it unitless, we convert to the standardization, and standardization means that we come up with a zero mean and unit variance. Once that is done, we go at the covariance matrix calculation. Now covariance matrix relationship establish the relationship among the variables. Are they independent of each other or they are independent, and if they are dependent, what kind of dependency is there? That's what important to us. So provide information on how variables vary together. Then comes a eigen decomposition, because eigenvalue problem has been solved in number of times. Here we do the eigen decomposition of the matrix or covariance matrix. Once that is done, we get eigenvalues and we get an eigenvector also. Then how do we select the principal component? We say to select the principal component, what we do, we sort the eigenvector based on corresponding eigenvalue. So higher value on top, lowest value will be on the bottom. Retain a subset of the principal component with the highest eigenvalue of the dimension. Now we say overall eigenvalue 95 percent, I'll go ahead, and last 5% I'll reject. That's a possible. So this is where we choose response. Here, as I say that the selection of principal component analysis will be based on that. Finally, which is difficult, is a projection. How do we project on the lowest dimensional space? That's a challenging. So that's why we say initially we got a some data set. Then we are going to go ahead with a transformed data set. Resulting database, whatever is coming from reduce a lower dimension. So instead of 10 variables, now we will go with 3 variables. Actually data set has to be changed when we are trying to correlate with this, and that is a major difficulty. Transform database, we will make it same database by transforming it so that it is related to only 3 parameters as I mentioned, compared to the 10 parameter which was earlier given. So what is the major limitation of the PCA? Is a basically linear relations. In non-linear it will not work. So that's why I say it may not be suitable for the database with a non-linear patterns. So this is the one of the limitation. Now try to because this principal component analysis has been documented in literature and available in online and many. So I'm just picking up one slide from the Duke Universities, where the principal component analysis has been defined on PDF file. You can download it also. Now in this case, what we are saying that initially the data has been given x and y, and then we are trying to introduce some other variables u and y. So initial variable x and y. Now new variable is a u and v. Now u and v has been changed. So what we say, initially determine the covariance matrix for standardized data. So first is the standardization is done. After the covariance matrix to connect it. Now here the data whatever has been given, we can digitize it, we can come up with the numbers. And then after that we go with eigenvalue decomposition, or we find out eigenvalues and eigenvectors by going with the eigen decomposition or covariance matrix. We sort eigenvalues from top to bottom in decreasing order to find the element of the importance. And then we say that choose a number of the principal component to be retained and recast data. This is what I mentioned in previous slide. This is a very tough, difficult task. Which variables means what, that need to come up, what kind of relation, what is the name should be given. Again, as I said that PCA is only applicable for linear relation, it may not work for the non-linear relation. Now here what I am trying to show, here it has been recasted. If you look at here that by doing PCA, after doing the PCA and dimensional reduction, we are getting importance of u and importance of v is 0, almost 0. You can see here the data here in this case there is a above below both sides, while in this case is more or less are getting aligned to the line. That means importance of the v is almost negligible. The variable v I can neglect. I had to go ahead with only one variable, that's a u, it is affecting, and that's the matter thing. Now how do we recast in x component of x and y, and that is where a little challenge come, because we need to change whole data set based on that. However, dimensional reduction has been shown very clearly. Here we have only u important, v is not that important, because instead of going for x y 2 dimension, we'll be going with only u dimension, that's a one dimension, that's a dimension reduction. So it helps in a big way. And this is a what the PCA. And with this I say thank you for attending this lecture. Thank you.